Okay, we're going to start looking at terminating decimals. So before we begin, just a quick warm up. Just glance at this picture. Now look away, look away. What portion was shaded purple? All right, so this is working on your visualizing and trying to see how you can break up a whole into different parts and compare sizes. So it's really a good activity to help build students' number sense by giving them limited opportunities to stare at a picture, but to let them kind of think on the spot. So if you looked away and then thought about the portion, if not, that's okay. We can still look at the portion. So I'm going to break it up. And so one thing that I noticed when I quickly glanced at this was that there were four triangles that were the same size. So I noticed in my quick glance those four guys, and then I noticed that what was left over was about the same size. So I quickly just filled this in kind of in my head, and so there were a total of 6 of the triangles that were that size. So that purple one I could see is 1/6 of the picture. So there might be more than one way to think about it, but that's how I thought about that. And so what that is, and what you would do like in your class, is called a number talk, or in this case, a fraction talk. And that was the source for that activity, or for that quick warm up. So we're going to get into decimals. And so in order to talk about decimals, we have to kind of go into our place value. And so one of the words, just the beginning word with decimals, to kind of see where that comes from, it comes from decem, which is Latin for 10. And maybe that part actually looks more familiar than decimals, for the month of December. Even though it's our last month of our year, which has 12 months, in around 750 BC, the year went from March to December, which would have made it the 10th month. So just some familiarity with it. And so what decimals are is breaking up our place values. So when we're looking at decimals, we have the regular place values that we're used to when we're talking about whole number values. We have like the ones, which we could write that as actually like 10 to the 0. And then we have the tens, which is like 10 to the 1. And we have the hundreds, which are 10 squared, and then 10 cubed, 10 to the 4th. Remember, every group of 10, you jump up to a 10 because that's our number system. We're in a base 10 system. So this would be 10 to the 5th and 10 to the 6th. Now, if you look at the pattern that's going on, we're decreasing by a 10 every time. We're dividing by a 10, dividing by a 10, dividing by a 10, dividing by a 10. And so then when we divide by a 10 again, that ends up being 10 to the -1. That's one way to write that. Or we could say it as 1/10. Divide by 10 again, that's going to be 10 to the -2, or we could say 1/100, or 100th. Divide by 10 again, we get 1,000. That's the 1,000th. We divide by 10 again, then we're at 10,000. And then divide by 10 again, we're at 100,000. And so we would say the 100,000th, and then we would divide by 10 again, and we'd be at the millionth. So you could see with these place values, they all end with the, which is partially comes out the way we say our fractions too. And so if you go back to our first decimal written here, it wants us to write it in words. So like we get used to saying like 0.5, but when we say we want to write it in the word form, we want to write it in terms of its place value. So if we look at 0.5, I'm going to write that down on my chart. That's 0.5 like that, but really we would read that as 5/10. So we say 5/10. And then when we look at the next one, we're seeing 0.53, but really let's say that the correct way. That one is going one more place value over. It's going to our hundredth spot. And so we read that as 53 hundredths. Whatever place value you land on is the place value that you say. So when we look at the 532, that ends in the thousands, so we say 500. We read the number like normal, 500, 32, and now we say these are thousands. Then we have 0.5324. We go to the 10,000ths now. So we have 5,324 10,000ths. All right, and then we got one more on here, and that one actually has a number in front of our decimal. So that's going to be said like normal. That's our 24. Now, when we actually start reading with the decimal, we use the word and. So we're going to say 24 and, so that way we know that they're wholes. And then we'll read the rest like we've been doing. So we're going to say 24 and 53 hundredths. And really this word form is getting us ready for the fraction form, which maybe even the fraction form might make a little bit more sense to you. So when we flip the page, what we're looking at are these wholes that are broken up into parts. So if you look at this one little square, this we are actually going to call 1/100th, because there's actually 100 little squares. You can count it. It goes 10 by 10. So we're going to have 100 little squares in there. So that would be 1/100th. Now when we look at it broken up this way, that big long tall column, that's going to be a 10th. And again, that should make sense because we have 10 pieces breaking up our whole. So when we want to write the decimal and the fraction for each shaded part, let's start by writing the fraction. So if we look at the number of red spaces filled in, we have 2 10s here really, right? There's like a 10 and then another 10 and then there's 1, 2, 3, 4, 5, 6. So there's a total of 26 of those little guys, which are hundredths. So that's 26 hundredths. And so as I'm saying that, the place value, remember, we have our tenths place, then we have our hundredths place. And so this is going to be written as 0.26. That's 26 hundredths. So for the next guy, we have 1, 2, 3, 4, but this time they're tenths. So we have 4 tenths, which is actually going to be equal to 0.4. Now, something else to note is that even though they're written as tenths, if I would have split this up the same as part A and made it into 100 pieces, another way that we could see this, pretend all these lines are straight. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, another way to see those 4 tenths is actually as, okay, there's 10 hundredths here, 10 hundredths here, 10 hundredths here, 10 hundredths here. So we actually have 40 hundredths. So that's actually equivalent. I'm going to write it as decimal. These are equivalent to each other, which you might recall from elementary school, knowing that if there's zeros after the number, they don't really matter. They don't count because it could be reduced. But really, they're the same. So next we look at part C. Again, I'm looking at hundredths. So I have 10 here, 10 here, 10 here, 10 here. That's 40 plus 1, 2, 3, 4, 5. So I have 45 hundredths, which is 0.45 if we write it as the decimal. But again, we read it as 45 hundredths. This one, they kind of split it horizontally, but it's still just one of the 10 pieces, so that's going to be 1/10. So we'll write that as 0.1. For our next one, again, you could pause at any time and try these on your own and then check your answer. So if you are paused, pause. And if you came back, welcome back. And we have 1, 2, 3, 4, 5. So this filled it in. Again, there's 10 each direction. So that's going to be 50 plus, this is one less than the 10. So we're going to get 59. And these are the hundredths. As a decimal, that's 0.59. I got 3 this way, that's 30 plus the 1, so I have 31. These again are hundredths, which was 0.31. For this next one, I have, let's see, 1, 2, 3, 4, 5, 6, 7, 8 rows out of 10. So that'll be 8 tenths, which I'll write it as 0.8. And then the last guy here, that's 2 columns, that's 2 tenths, which is 0.2. Or again, I guess I could have said it, I'm sorry, as these are each little pieces. So there would be 10 in this row and 10 in that row. So that would make a total of 20, and these are hundredths now. And we could write that as 20 hundredths. But again, these have the same exact value, just different ways of breaking them up. They're equivalent. Now, another way to talk about the decimals besides these 10 by 10 boxes is to go back to our 10 pieces, but we have to redefine them. So if we start saying that this big block is actually our whole one, then each of these guys is really going to be a tenth because it takes 10 of them to make up that whole. So this one whole would be that guy. And then the littlest guys, instead of being our ones, those are going to be hundredths, since it takes one of those, or it takes 100 of those to make the whole. So if I want to represent this decimal in base 10 blocks with this redefined value, I'm going to have one of those, two of those. So this would be my 2 of my tenths. And then I would need 3 of these little guys because there would be 3 hundredths. So again, just two different ways of looking at these decimals and fractions. So looking at this next section, what we want to do is be able to express each of the following as a decimal. And so if you noticed on the previous page, all of our fractions that we came up with were out of 10 or out of 100. And I think that should make sense with the words that we're saying, because we have our tenths, our hundredths, and we have our thousandths. And so what we kind of want to do is be able to write each of our denominators as basically a power of 10. So we need to have the denominator as 10 to some power. But just a little reminder that this is the same thing as saying I need to have 2s and 5s in my denominator. So our exponent rules would say 2 to the n, 5 to the n. So if we have that in our denominator, then we really have some power of 10, which means we can write it as a terminating decimal. Terminating meaning it has like an end. So when I look at the number 1/25, some of you guys right away can say, how can I turn that into something out of 10 or out of 100? But when I see the 25, I think about how that is 5 squared. So if I look back over to what we were talking about, I need to have like 10 in there. So I already have 2 5s. I would need 2 2s. And so if I want to put 2 2s in there, I could put them in the bottom as long as I put them in the top as well. So this is going to end up being 2 squared times 1. So we get a 4. And on the bottom, we have 5 squared times 2 squared. We can rewrite that if you want to see it as a power of 10 to the 2 power. That's 4 out of 100. Or we could read that as 4 hundredths, which will be equal to 0.04, written as a decimal. And so we can continue on. Let's see, 250. That is 25 and 10, and we have 5 and 5, and we have 5 and 2. So if you look at this, we have 3 5s. We need to have the same number of 2s. So again, we're going to need 2 squared again, 2 squared. So this will be 7 times 4, so we're going to get 28 on the top. On the bottom, we're going to get 2 times 5. There's 3 sets of those. So 28 out of 10 to the cube. So that's 28,000. So 28 thousandths will be equal to, remember it's the tenths place, hundredths place, thousandths place. So we're going to have to write 28 thousandths, which means we fill that in with a 0. And again, all of these you can double check on your calculator. You just have to enter 7 divided by 250, and it should give you that decimal. 1 divided by 25, and it should give you that decimal. But you need to know why and how this is working. So for part C, I have a bunch of 2s, 2 to the 6. That's a lot of 2s. Now I need an equal number of 5s, so that way I can talk about 10 to some power, which would be a 6 here. And this is 5 to the 6th. So when I take 7 times 5 to the 6th, well, that ends up being 109,375. So that's 109,375. really out of a million. 10 to the 6 is a million. Quick way to get that, by the way, 6, it's multiplied by 10 6 times, which ends up getting you 6 zeros. So I have 0 point, I have tenths, hundreds, thousands, 10,000s, 100,000s, and millions. Since I need to end in that millionth spot, I'm going to kind of write the number backwards, just so that way if there's any zeros to fill in, 5, 7, 3, 9, 0, 1, if it's perfect. But if there, again, was a number not in this place, it would need to be filled in with a 0. That placeholder is essential. So now I'm looking at part D. I have 3 2s and 4 5s. I need just one extra 2. And so this is going to be 2 over 2 to the 4th, 5 to the 4th. So 2 times 5 to the 4th. Or you can say 2 over 10 to the 4th, which is 2 out of 10. Let's see, how many 4 zeros there? 10,000. So 2 10,000s. So again, that's tenths, hundreds, thousands, 10,000s right here. And so we need to end there with the 2. So then that would fill in with zeros. They act as placeholders that are necessary placeholders. So what we're seeing from above is actually turned into a theorem. And that theorem says that a rational number a over b is if it's in simplest form, can be written as a terminating decimal if and only if its prime factorization of the denominator contains no primes other than 2 or 5. And you could have seen from up above, that was all we had was the 2s and 5s because we wanted to write it as a power of 10 in order to write it as a decimal. So if we look at the number 2 over 11, since 11 is not a power of 2 or 5, it's prime actually, we know that it's not a terminal decimal. And if you punch that in on your calculator, 2 divided by 11, you can see that it is equal to 0.1818181818. It ends with a 2, but that's actually just a rounding that your calculator does. And we're going to see that in one of the next lessons, that that's a repeating decimal. And so it does not terminate. So let's look and see. We're supposed to explain which of the following can be represented as a terminal decimal. So we have 7 8s. So 8 is 4 and 2 and 2 and 2. So looking at our denominator, they're all powers of 2. So we are good. We can write that as a decimal, a terminal decimal. Because really it would just need 3 more 5s to match up. Now I look at 11 over 250. This is 25 and 10, 5 and 5, 5 and 2. And again, we're good because we have 3 5s, 1 2. Really, it would just need 2 more 2s in order to make a power of 10. So we're all good with that. 21 over 28. Well, 28 is 7 and 4, and then that's 2 and 2. And so I have my 2s, but the 7 looks like it's messing things up. So I'm going to say no, but then, oh, wait a minute. If we look at the numerator, this fraction is actually not in simplest form. 21 can reduce. This is actually 7 times 3 and 7 times 4. So that 7 that was causing the problem, this can actually be written as 3/4. And so that 4 is 2 times 2. So we have those powers of 2. So we can add in 2 more 5s and we'll be able to write it as a power of 10. And some of you guys already know 3/4 is actually 0.75. So that one's okay too. So let's look at this last one here. We have 37 over 768. So this is 2 and 384. This is 2 and then 192. Keep dividing by 2 because that's easiest on my calculator here. 2 and 96, 2 and 48, 2 and 24, 2 and 12. Lots of 2s, so that's a good sign. 6 and 2. Uh-oh, here we go. Here's 3 and 2. So the 3 here is not a 2 or a 5. There's no way to turn it into that. So let me just double check that it was in simplest form. So if this 37 can be divided by 3, then it would be able to be written as a terminal decimal. Now 37 can't be divided by 3 because its digits, 3 plus 7 equals 10, which that means that 3 cannot divide the 10. So 3 cannot divide the 37. So this one cannot be written as a terminating decimal. And if you enter in your calculator, 37 divided by 768, you'll get something that kind of looks like it terminates, but we'll see in the next section that it won't, and a way to find out what they are. So according to that theorem, because our 3 is not a power of 2 or 5, it will not be a terminal decimal. Okay, flipping the page, we're looking at this excerpt from a student book. It actually comes from page 357 of your book, and it's actually from 4th grade math, and it's comparing or ordering decimals. So when we're comparing decimals, there's some common misconceptions that happen, and actually part of your homework is to watch a video of a student making one of those misconceptions, so be sure to check that out. But let's try and see if we can compare fractions by using these grids and also these base 10 blocks. So the first part, it's the example that this textbook gives is it compares this 23 hundredths to 32 hundredths. And so based off of the picture, you can see there's 2 of the tenths and 3 of the hundredths. So there's your 23 hundredths. And visually you can see, oh, that one has 1 more tenth. So of course that has to be the bigger one. If we look at our guided practice here, it says to critique the reasoning. So Sai says 0.20 is greater than 0.2 because 20 is greater than 2. Now let's say this correctly. This is actually 20 hundredths. You can write it as a fraction if you want to. And this guy right here, 0.2, is actually, let's say it correctly, 2/10. So I kind of see what they're saying about, okay, the number 20, yes, is bigger than the number 2, but you're comparing 2 different size pieces. So this is where a picture is really helpful. So 20 hundredths, if I'm imagining the grid, that was 2 of the lines in the grid. So when we were breaking it up into those 10 pieces, we were talking about 2 of those lines. Now when we're looking, because there were 10 in that one and 10 in that one. I guess that would be the fastest way. So if we broke it up, you can kind of see below for a second. I'm going to steal one of these grids. So 20 would be coloring in 20 of these. So we know there's 10 in a row. So that's why I said 2 rows. But there's your 20 hundredths. Now if you look at this 0.2, which is 2/10, that's totally 1 whole row, 2 whole row. That's 2 of the tenths. But look at, they're actually equal to each other. So just because you see the number 20, you need to think about what size the pieces are. So we're going to erase these boxes because we're going to use them in a minute. But I hope that makes a little bit of sense. So what we want to do next is look at comparing, we'll look at number 2 here. 70 hundredths with 57 hundredths. Even just saying the words might be helpful. But again, the place value of this is 70 hundredths. So that's going to be, here's 10, 20, 30, 40, 50, 60, 70 of the hundredths. And I want to compare that to 57 of the hundredths. So visually you'll be able to see there's 40, there's 50, and there's 7. So I have 57 hundredths. So comparing them, for sure the 70 hundredths is bigger. For part 3, we want to compare 41 hundredths, and this they kind of flip-flop the digits, trying to mess with you a little bit. And so it's just showing that the order is really important. So there's 30, there's 40, there's 41 hundredths. We want to compare that to 14 hundredths. So 14 hundredths. And so again, visually you can see that 41 hundredths is bigger than having 14 hundredths. So we're going to have our inequality like that. For parts 4 and 5, let's look at the place value blocks for that. So when I'm looking at number 4, it says 6 and 28 hundredths. So I'm going to compare 6. So I have to have those whole guys. I'm going to have 6 of them. And then I'm going to have 28 hundredths, so 2/10, and then 8 of the little hundredths. I want to compare that with the 7, which right away I'm like, oh, look at the holes. The holes are bigger. These ones aren't making a hole, so this has to be more pieces, not more pieces, but a larger number than the 6. So we can see that it's more mostly because of that whole number. When we want to compare those next two, let's do it on this side here. We have one whole, so both of these are one whole. Okay, so let's compare that. There's one whole. And then the left side there, that's 1/10. So that's going to be one of those guys. And then this says 10 hundredths. So 10 of those, 4, 5, 6, 7, 8, 9, 10. But really, this makes 1/10 here. So that means these are going to be equal to each other. And that's all we have.